Okay, in this little video, I'm going to do the derivation of the cosine rule. So we've seen the cosine rule today. I'm going to show you here how it's actually derived. Now, this is pretty tricky. It's not for the faint-hearted, so you may need to stop the video and go over various bits. That's okay. Yeah, so it's really only for those that are super interested in knowing where it comes from. Okay, it uses a fair bit of algebra here as well. All right. Have a look at the diagram that I've drawn there. There's a triangle. We've got this perpendicular here, H, A, B, and C, as we did for the sine rule. So there's our angle A, and opposite is side A. Angle C, opposite is side C. Angle B and opposite it are broken. Well, the perpendicular is broken side B into two parts. And so one of those parts I've called X, so just that length from A through to where the perpendicular connects. And then this, if that's X and this whole side is B, then this bit in here must be B minus X. And that makes sense because when you add B minus X and X, what happens with the X's? They disappear and you're left with B. Okay, so let's start. Now, the cosine rule uses Pythagoras' theorem. And so remember, Pythagoras' theorem says that the hypotenuse squared is equal to the sum of the squares of the other two sides. So we're going to do the same sort of approach as we did with the sine rule. We're going to work out an expression that involves that perpendicular. We're going to use the two right angle triangles that we've got here we'll use Pythagoras' theorem on both of those right angle triangles, and we'll use Pythagoras' theorem to come up with an expression involving H in two different ways. Okay, so let's start with let's just start with the triangle on the left-hand side. And so if I used Pythagoras' theorem there, I would get that the hypotenuse, c squared, is equal to h squared plus x squared. Okay, so I said there's going to be a bit of algebra. Here's the first bit, and that's an algebraic expression. And what I want to do is rearrange that algebraic expression so that h squared is the subject. And so remember, when we shift things around in equations, we can do it very easily. We've just got to remember that when we move things from left to right, or whenever they cross that equal sign, they change sign. Okay, so here on this right-hand side, I've got a positive x squared. If I move that across to the other side, I'd get a negative x squared. So if I'll do that, I'll move that x squared across. That gives me c squared minus x squared equals h squared. So basically it's the same expression, but h squared is the subject. Okay, now let's turn our attention to the other triangle, the other right angle triangle. I'll do the same thing using Pythagoras' theorem. And so the hypotenuse, a squared, is equal to h squared plus the other side, which is b minus x. So that'll be b minus x all squared. Okay. And again, I want to make h squared the subject, and so I'll have to take that b minus x squared across to the other side. That means it'll become negative, and so I'll get a squared minus b minus x squared equals h squared. All right, so I've got two different expressions there. Just highlight those. And I've got this expression and this expression, and note that they're two different expressions, but they're talking about the same thing, aren't they? H squared here is equal to c squared minus x squared, and down here we've got h squared is equal to this other complicated thing. So if h squared is equal to both of them, then those two expressions must be the same. there must be different ways of expressing the same thing, okay? And so what we can write then is that therefore c squared minus x squared is equal to a squared minus, brackets, b minus x squared. Alright, and that's what we're going to use next. We've got to work out what all of this means. Okay, so what I'm going to do now is look at that right-hand side, and the thing in brackets there, the b minus x squared, I'm going to expand that. Now, if you remember back to our first unit that we did this year, we looked at these types of things. This is called a binomial. It's a perfect square, and we know how to expand that. Remember, you take that first term, the b, and you'd square it. The minus x, we'd square that. And the b and the minus x, when we, we multiply that and double it. Just to remind you what we do, b minus x squared, I might do it over here on the side, just as a little reminder. B minus x squared, let's do it. B minus x squared is equal to, get lost, calendar. Why is that even there? Is, there it is. Right, okay, b minus x squared is equal, well, whenever you square something, it's itself, well, you're timesing it by itself, so it's b minus x times b minus x, and then remember we go b times b, that's b, oh, come on, get lost, b squared, there'll be a b times minus x, so that's minus bx, there's a minus x times a b, so minus another bx, and then a minus x times a minus x is a plus x squared. Okay, and when you tidy that up, you've got a b squared. Now there's a minus bx minus another bx, that's minus 2bx. And then you've got this plus x squared on the end. Alright, so that expression there is equal to that thing, b minus x squared. So let's do all of that. We've got c squared minus x squared. Same thing on the left, equals a squared minus, and then in brackets here, I'm going to replace all of that b minus x squared with what we've got over here, on the, over here, this expansion. B squared minus 2bx plus x squared. Okay, so that's looking pretty horrible. Let's keep going, and we'll try and get rid of those brackets. C squared minus x squared equals a squared. Now, everything in this brackets, there's a minus sign out the front. So it's going to be minus this first thing, so minus b squared, and then minus 2bx, so that's plus 2bx, and then minus plus x squared is minus x squared. Okay, alright, so what do I do with that? Well, what I might start by doing, well, what I'll notice is that, okay, on the left-hand side, I've got a minus x squared. So I'm doing a bit of trickery here, algebraic trickery. On the right-hand side, there's also a minus x squared. Alright, what can we do with algebraic expressions that have exactly the same thing on both sides? Well, we can get rid of them, and that'll help tidy things up. If I added x squared to both sides, that wouldn't change anything. I'm adding exactly the same thing to both sides. That's what I'm going to do. I'm going to add x squared here, add x squared here, and what's going to happen? Well, they'll cancel. You've got x squared minus x squared on the left, and x squared minus x squared on the right. Those x squareds are just going to vanish, and that'll help tidy things up considerably. That'll give us c squared on the left is equal to a squared minus b squared plus 2bx. Right, so that's a bit simpler. Now, just because I want to be pedantic, I am going to make a squared the subject, purely because it's the first letter in the alphabet. Right, so that means I'm going to move things around. The minus b squared is going to come across to the left, And because it's minus b squared and it moves to the left of the equal sign, it's going to become plus b squared. The plus 2bx I'm also going to take across, and that's going to go negative because it's positive on this side, it'll go negative on the other side. So I'll end up with, on the left hand side, b squared plus c squared minus 2bx equals a squared. Alright, and I might even flip that around and write it like this. A squared equals b squared plus c squared minus 2bx. Okay, so we're nearly there. I might just make that smaller, some of this stuff. Just give me a sec. Just to give myself a bit of room. Okay. How's that? Okay. I'll do the same down here. Right. Okay. So, now, the only last, see, if you look at this expression here, it all makes sense apart from the x, okay? We know what a is, well, a is one of the sides, b is one of the sides, c is one of the sides. X, well, we don't really know what x is. X could be anything depending on the shape of the triangle. So, how can we go about finding x? Well, let's look at this left-hand side right angle over in the diagram. We've got three sides, one's C, one's H, one's X. What I'm going to do here is I'm going to just focus on this angle A. If we were to, let's assume that we knew what C was, and we knew what that angle there was. Is that enough information to work out X? Well, yes it is. X would be the adjacent side to angle A. C would be the hypotenuse, and the ratio that would use the adjacent and the hypotenuse would be cos. So cos theta, theta in this case is angle A. Cos of A would be adjacent on hypotenuse, which would be x on C, and so therefore x would be C times cos A. Okay, well, that gives us an expression for x. Now, if we just put that straight into this expression, we're going to get a squared equals b squared plus c squared minus 2b, and instead of writing x, I'm going to write c cos A. And that is the cosine rule. It's a very interesting rule because you can think of it as a generalization of Pythagoras' theorem. If A happened to be a 90-degree angle, what would happen to this? Well, remember cos 90 is 0, and so all this 2bc cos A thing would become 0. It'd vanish from this formula, and you'd be left with a squared equals b squared plus c squared, which is Pythagoras' theorem. So it's sort of like Pythagoras' theorem for non-right angle triangles, which sort of sounds weird because I've always said that Pythagoras' theorem was just for right angle triangles, which it is, but this is a generalization. Okay, there we are. That's it.